I welcome you all in this presentation related with the subject materials processing fundamentals and practical. And we are talking about welding of metals, and this is the continuation of the previous lecture where we talked about the welding metallurgy associated with the fusion welding process. In this particular presentation, I will be talking about the welding metallurgy related with the solid liquid joining process and solid state joining processes. Okay. So, as far as the content is concerned, we have the welding metallurgical aspects of the solid liquid joining process like the brazing and soldering, where parent metals are remain in the solid state, but the low melting point brazing or soldering material is brought to the molten state. This molten material interacts with the parent materials in the solid state and forms some kind of the intermetallic compound at the interface, and that helps in developing the metallurgical bond. In solid state joining process, primarily plastic deformation coupled with the diffusion is involved, and that in turn leads to the multiple kind of the metallurgical transformations. Okay. So, we will be talking about the kind of the metallurgical transformations which occur in the solid state joining process. Then the carbon equivalent and its significance, this is particularly true for the welding metallurgy associated with the hardenable ferrous metals, or we can say ferrous metals which are hardenable. Okay. Then what are the common issues which are encountered? So, the relationship between the carbon equivalent and the ease of welding the ferrous metals. Okay, since the carbon equivalent is related to the ferrous metals or work transformation hardenable metals like steels, and therefore, you will try to see the relationship between the carbon equivalent and the weldability of the ferrous metals. Then what happens when the carbon equivalent is very high? Many issues are encountered and that pose many challenges in development of the good weld joint with reasonably good performance. So, how to deal with those issues in case of the high carbon equivalent ferrous metals? So, what are the strategies that are available? Okay. So, now going ahead with the solid liquid joining process, like in the brazing and soldering, say the parent metal A and B. So, initially what we do, the surfaces need to be clean and prepared, then heated, okay, using suitable source of heat. This can be induction heating, this can be flame heating, or this can be any other kind of heating. When things are heated, the metal surfaces interact with the atmospheric gases. So, they tend to form the oxides, nitrites, and also impurities can be there at the surfaces. To take care of these impurities, normally the flux is applied at the surface, so that when the flux is there, it interacts with the impurities to form slag, that is one. Additionally, it improves the fluidity of the molten metal that is being obtained by melting the brazing or soldering material. Okay. So, since the brazing and soldering material are relatively low melting point materials, therefore, when a brazed or soldered joint is developed, we get the relatively low strength as compared to that of the parent metal, because the melting temperature is less. So, strength is also lesser than the parent metals. Okay. But if we see, say a joint has been developed, a brazed joint has been developed. Okay. So, another thing which is important here, like this is the one substrate of great thickness, like, and this is the another substrate or another parent material, and in between we have the molten brazing or soldering material. Okay. So, heat is extracted very rapidly to the underlying parent metals. So, how the liquid to solid state phase transformations occur in the brazing or soldering process? It is very simple. Initially, we may get some kind of the planar thing, and mostly it is the cellular grain structure which is obtained in the after the solidification in the brazed or the soldered layer. This is one aspect. The second one is where the molten metal will be interacting with the parent metal A and B. So, it is possible, like if the filler metal used for brazing or soldering purpose is C, then C can interact with the A differently from the B. Okay. So, there is a possibility that when the C interacts with A, it forms one kind of the intermetallic compound, and when C interacts with the another parent metal, it forms the another kind of the intermetallic compound. So, when this kind of joint say has been formed, where we have one parent metal, another parent metal A and B, and then one filler metal as per the process, whether it is brazing or soldering filler, and then two additional zones are formed like intermetallic zone A and intermetallic 2 with the another parent metal. Now, when the load is applied, say tensile shear load is applied, what happens? That the failure will occur. Okay, on increasing the load, increasing the tensile shear load, the failure will occur. Failure can occur from the 5 different locations. It can be parent metal B or it can be parent metal A. Okay, it can be the solder material. This is the another zone. So, 1, 2 and 3. Thereafter, the failure can also occur from the interface between the parent metal A and the soldering or brazing filler, that is interlayer intermetallic being formed, intermetallic A we can say. A failure can also occur from the intermetallic B. Okay. So, we know that the joint is just like a chain. Whenever load is applied, so the weak link will fail. So, which is the weak link that will trigger the fracture. Okay. So, say when the load is being applied, failure can occur from the parent metal B, or failure can occur from the parent metal A, failure can occur from the soldering material or brazing filler, or failure can also occur from the interface of the filler with the part A or interface of the filler with the part B. Whichever is the weak, that will fail. So, say if the part B is failing, means the joint and the part A both are stronger. If the part A fails, which means the part B is strong, but the part A is weaker than the joint and the part B. Okay. And there is another possibility, that is like if the failure occurs, mainly load is applied and failure occurs from the filler metal itself, then interface is intact, both the sides, parts A and part B both are intact, means they are stronger. Okay. And the filler is weak. Okay. So, by changing the filler, it will be possible to increase the joint strength, that is one of the aspect. Okay. And this is also possible, like if the failure occurs from the interface intermetallic A, that is the filler and the part A interface. If this is failing, means this intermetallic A is weaker. Okay, or intermetallic B is weaker if it fails from the other side. This B is weaker. So, that makes the problem little difficult, like it becomes the case where we have to modify the intermetallic or modify the intermetallic B in such a way that it has the more favorable characteristics, and most of the time what we get the hard and brittle intermetallic compounds. So, if it is very hard, very brittle, then this will lower the load carrying capacity, lower the ductility, okay, of the brazed or soldered joint which is being formed. So, what is done in order to modify the characteristics of the intermetallic being formed on the A side, intermetallic A or intermetallic B, we can do lot of things. It includes like the post heat treatment of the joint, or it also includes the modification of composition of the IMC which is being formed. So, that can be there by choosing the suitable kind of filler or by incorporating certain alloying elements with the filler. So, that help in developing the more appropriate kind of the intermetallics wherever from the failure is getting triggered. Okay. Now, as far as the solid state joining process is concerned, in the solid state joining there are two broad approaches. One is the plastic deformation, which can be both micro or macro level, okay, coupled with the like the heat generated will be causing the recrystallization or the grain growth or recovery or the deformation assisted phase transformation, apart the grain refinement due to the dynamic recrystallization. That is, this is one thing. where deformation coupled with the heat causes many changes. Okay. Another one is where just the diffusion is involved. Okay. So, like in the diffusion bonding process where primarily at the surface we may have micro level plastic deformation, but mainly the diffusion across the interface is responsible for the development of the joint. So, if we talk of the processes like friction welding, friction ester welding, forge welding, okay, ultrasonic welding, explosive welding or our magnetic pulse welding. In these processes certainly the plastic deformation is involved coupled with the little heat generation. Okay. So, if the metal is significantly work hardening type, then the micro level plastic deformation at the surface leads to the increased hardness. So, if we talk of like say ultrasonic or explosive welded joints, then the two sheets being joined by the ultrasonic or explosive welding, then at the interface multiple morphologies can be formed at the interface. One is simple where it is flat coupled with the micro scale plastic deformation, another is wavy structure, third is jetted, fourth is jetted coupled with the melting at the root of the these jets which are being formed. So, but in all these cases what is common? Significant plastic deformation at micro level, okay, and when this plastic deformation occurs in the work hardening metal, then there is a significant increase in the hardness. Okay. So, this we can say this can be due to the simple strain hardening, the grain refinement or the plastic deformation assisted transformation. So, multiple factors can be responsible for little higher hardness, because the heat generated during the ultrasonic and explosive welding is very limited. Okay. So, at the same time let you see if the metal is primarily the precipitation hardening kind, okay, then the work hardening and the recovery and recrystallization, all these things, effect of all these things will be very limited. Okay, and there is no scope for formation of the fresh precipitates, rather due to the heat generation it is possible that some reversion can take place, and that can significantly reduce the kind of the interfacial hardness distribution that will be observed in case of the. So, this may be true for the WH metals, work hardening metals, and the another one can be true for the precipitation hardening metals. Okay. Now, if we talk of the solid state joining process where significant plastic deformation is involved, like the FSW, okay, friction ester welding. So, in case of the friction ester welding of the precipitation hardening metals, these metals are strengthened by the formation of the fine precipitates in the matrix. So, when the plastic deformation is carried out, metal is severely deformed coupled with the heat generated, and heat generated is also significantly high to cause the reversion, okay, in the weld nugget area. So, the two things happen, one is severe plastic deformation coupled with the heat generation that will be causing the. So, severe plastic deformation coupled with the heat generation causes the dynamic recrystallization. This dynamic recrystallization forms the new fine and recrystallized grains, where from everything has been eliminated as far as the precipitates are concerned, everything has been dissolved. So, due to the dissolution of the precipitates, obviously some effect of the elements that are going into the solution, maybe they are in form of the solid solution strengthening, but since these are the precipitation hardening metals, so there will be a drop in hardness and strength. That is what we can see in the weld nugget, there is a drop as compared to the base metal. What are minor greater hardness that we can see? So, there is a drop as compared to the base metal, there is a drop in hardness and strength, and this is attributed to the like loss of precipitates. Okay. But this loss is much more severe, but apart from this loss there will be little work hardening effect, there will be little grain refinement effect, because the weld nugget is severely deformed coupled with the heat generated. So, we get the dynamic recrystallization, and which will be leading to the fine grain structure. At the same time some work hardening effect can also be observed, but if we see the zones which are little away from the nugget zone, those which are not falling in the nugget zone, but say this zone which are away from the nugget zone, okay, little away from the nugget zone. In that area, you see this area which is significantly being affected by the heat, there will be severe drop of the hardness, and that is attributed to the complete reversion coupled with the grain growth, no work hardening effect whatsoever it is. And that is why even in pH metals we get the little higher hardness due to the grain refinement and the work hardening effect, but in HZ there is a significant drop due to the reversion, complete loss of the precipitates coupled with the grain growth, no work hardening effect, and that is why the minimum hardness zone is found in the HZ zone of the pH metals which are subjected to the solid state joining process like friction, stir welding, and that is why what we see here, like in the nugget zone A, the weld nugget is refined due to the dynamic recrystallization, but it is completely free from the any kind of precipitate. So, the all dissolved zone is formed. Complete reversion and grain growth takes place in the zone B, reversion is partial with the little grain growth in the zone C and a recrystallized grain in the D and unaffected base metal. So, that is why we will see that thereafter after the B zone we have the increasing hardness and the strength. Okay. So, this is about the precipitation hardening metals where significant plastic deformation is involved, and that will be coupled with the heat generation, enough heat generation which is able to cause the recrystallization of the metals. If we talk of the solid state joining process associated with the work hardening metals, then the kind of metallurgical transformation that can occur. So, say ferrous, if we talk of the steels, then they also show reasonably good work hardening characteristics coupled with the transformation hardening. So, solid state joining like FSW of the ferrous metals, what it causes, significant work hardening of the weld nugget area coupled with the transformation assisted hardening, because initially we may have the ferrite and pearlite at room temperature, but the kind of weld thermal cycle imposed during the welding that usually leads to the formation of martensite coupled with the some pearlite, and therefore we get significant higher hardness in the weld nugget area of the ferrous metals. Same is also true for the WH metals, since these metals rely heavily on the work hardening, and since the weld nugget area is subjected to the severe plastic deformation, and therefore this zone will be showing the significant increase in hardness and the yield strength. Okay, that is why we get the significantly higher hardness of the weld nugget area. Away from that, whatever zone is being formed, like say, since the work hardening metals are strengthened by development of all these dislocations. So, the metals to these metals through controlled plastic deformation, we try to realize the high dislocation density, so that the yield strength and hardness can be enhanced. But when the solid state joining process like FSW is carried out, the heat generated during the FSW is dissipated to the underlying base metal, and that in turn causes the loss of dislocations. So, recovery predominantly occurs in the heat affected zone. So, it is basically the recovery that causes the loss of these dislocations, and that in turn causes the significant drop in the zone B of the joint, which is of the joint of the metal which is work hardened, okay, or strengthened by work hardening. Okay. So, the ferrous metals respond very rapidly, significantly towards the solid state joining process, because not just work hardening takes place, but also the deformation assisted phase transformations also takes place due to the typical weld thermal cycle which is imposed. So, if we try to see here that the different zones which are formed in the WH metals, then the zone A, that will be subjected to the complete refinement of the grain because of the severe plastic deformation that will be experienced, coupled with the heat generation that can also cause the formation of the new grains. So, the dynamic recrystallization occurs in the weld nugget area, and even in the ferrous metals it can occur, the phase transformation hardening can also occur in this area. But if we talk of the other areas, the zone which is next to the weld nugget area, that will be experiencing the recovery and the grain growth, and therefore we will be getting the softening of the HZ in the work hardenable metals, and likewise because all these zones B, C, D are being formed primarily due to the heat generated, while the zone A is affected by the plastic deformation coupled with the heat both. Okay. So, other areas like B will be affected significantly by recovery and grain growth, that is why we will be getting the HZ softering. That recovery will be partial, little away from the nugget area and coupled with a little grain growth, and the recrystallization zone and unaffected base metal. Okay. So, this is about the kind of the phase transformation or building metallurgical aspects related with the WH metals. So, if we talk of the carbon equivalent and the weldability. Okay. So, the carbon equivalent is about what? Carbon equivalent is a parameter that shows the effect of various alloying elements present in the ferrous metal having the effect similar to that of the carbon. Okay. I will repeat it once again. The carbon equivalent shows the effect, combined effect of all the parameters which are having the effect similar to that of the carbon. Okay. So, if we have to calculate the CE, carbon equivalent, then we add the carbon atomic at the carbon weight percentage directly, then Mn, manganese is divided by 6, chromium, molybdenum, vanadium is divided by 5, and the nickel plus copper divided by 15, and depending upon the alloying elements present in the steel, this is used for the, this equation is used for determining the carbon equivalent of the alloy steels. Okay. If the carbon equivalent of the alloy steel is like say less than 0.4, means the transformation hardening tendency will be very less. Okay. And therefore, the issues related with the transformation hardening like embrittlement and cracking of the weld and HZ, that will be limited. Okay. Therefore, if we have the lesser carbon equivalent, then the weldability is high. If we have the higher carbon equivalent, then the weldability will be less. Okay. So, if we see in the x axis we have the carbon equivalent, say carbon equivalent is here, then the weldability is really very high. If go for the higher carbon equivalent, then the weldability keep on decreasing. Why? Because increased hardenability, increased preheat requirement to avoid the cracking and embrittlement. Therefore, the weldability will keep on decreasing, because we need extra care, extra precautions to develop a sound weld joint of the high carbon equivalent ferrous metals. Okay. So, the carbon equivalent is calculated using, say, for alloy steels using this equation, and we can see that the hardenability, weldability, preheat temperature requirement, cracking tendency, everything is affected by the carbon equivalent. So, weldability comes down with the increase of the carbon equivalent, other parameters like hardenability, preheating requirement and cracking tendency, and so all those decrease with the increase of the carbon equivalent, because it will require greater precautions, greater steps, greater more sophisticated procedures for development of the sound weld joint. So, if we see the typical thumb rules, if the carbon equivalent for a steel is less than 0.45, then we do not require much preheat, no preheat is required. If the carbon equivalent is in the range of 0.45 to 0.72, 0.7, then the preheat requirement can be from 200 to 500 degrees centigrade for carbon equivalent in the range of 0.45 to 0.7. So, preheat range is 200 to 500 degrees centigrade depending upon the carbon equivalent. Okay. This is particularly very effective to avoid the embrittlement and cracking tendency of the reducing the cracking tendency of the weld joint. So, the preheat requirement is less severe if the thickness is less, because the cooling conditions will be somewhat limited. But if we talk of the thick sheets, if we deal with the say welding is carried out of the thicker sections, then thick sections will be dissipating the heat very rapidly. It requires lesser carbon equivalent to ensure the transformation of the soft phases into the martensite, and therefore, the thickness factor is also considered with the carbon equivalent, and if that is considered, then we have additional parameter that is called compensated carbon equivalent. So, compensated carbon equivalent CCE is calculated using the carbon equivalent plus the thickness factor 0.0425 T. T is the thickness of the plate in mm, and in that case the empirical equations used for taking a call on the preheat requirements. So, if we have like it in the range of, if the CCE is less than 0.4, then no preheat is required. If the CC is in the band of 0.4 to 0.7, then preheat of 200 to 500 degree centigrade may be used to avoid the embrittlement and cracking tendency. And if the CC is greater than 0.7, then the steel is considered to be not weldable, okay, or it requires extra precautions for development of the weld. For low carbon steels, for microalloy steels, CC is obtained using this formula C, because multiple equations have been proposed. So, the C is obtained from this equation, and from the welding journal for low carbon microalloy steels, this is given by the another equation. Okay. So, we can calculate the CE, and we can accordingly we can take a call on like what kind of the preheat should be given. Usually we have the direct relationship between the carbon equivalent, like say ranging from 0.3 to 0.8, okay, and here we have the preheat temperature requirements. So, this preheat temperature increases continuously with the increasing the CE, okay. So, this direct relationship is particularly used for the certain kind of the compositions, okay. So, what is that, if the carbon equivalent, say carbon equivalent in range of say this one up to 1, and if the steel composition is falling in this zone 1, okay, then this is considered to be easily weldable, because here carbon content is less than 0.1 in general. Weld zone 2, if we see the weld zone 2 is one where the carbon content is greater than 0.1, and the carbon equivalent is also like in the band of say 0.2 to 0.5, okay. Carbon content is greater than say 0.1%. So, this is zone 2. In this zone, by using this CE and preheat requirement relationship, we can still develop the good joint. The zone 3 is considered to be non-weldable, which requires extra precaution to avoid the cracking and embrittlement. Okay. So, here carbon equivalent is greater than 0.5 and carbon is also greater than 0.1. So, that falls in the case of the zone 2. So, to avoid the cracking and embrittlement tendency, you see, for zone 1 and zone 3 Gravely diagram, which classifies the various types of the steels based on the carbon and carbon equivalent, and how to deal with those issues related with these steels falling in the different zones. So, if we see the carbon equivalent calculated using this equation, then we have one cracking parameter which is calculated using this set of the equation, and we get one PCM which is calculated using this equation, okay. And then weld distance is also considered, where in K naught multiplied by H, that gives H is the combined thickness in mm and K naught is a coefficient. So, using these various parameters PCM, K naught, what we can do is we can determine the preheat temperature to be used using this equation to identify the kind of preheat temperatures to be used for calculating the for avoiding the cold cracking. Now, I will summarize this presentation. In this presentation, basically I have talked about the various metallurgical transformations that occur during the brazing and soldering and solid state transformation, solid state joining process, like the friction stir welding of the pH and work hardening metals, and also the effect of the carbon equivalent on ease of the welding of the ferrous metals. Thank you for your attention.